Hi everybody, welcome to the first video of chapter 3.1, remainder theorem and factor theorem. So we're going to talk about synthetic division and let's remind ourselves what we know. So we're going to use synthetic division to divide this polynomial by x plus 4. So remember, we're going to have this box and we're going to have some coefficients here. So how do we fill this all out? So the first thing I do is I take what we're dividing by, x plus 4, and I kind of zoom in. This is my little side note over here. So x plus 4, what I do is I set it equal to 0 and I solve for x. And we get x equals negative 4. So this is going to go in like our little box. So I kind of box it off, okay? And now we're ready to fill in the rest of our synthetic division. So this first line here represents the coefficients of our polynomial. So we have a 1, we have a negative 4, we have a 7, and we have a 15. But what we notice here is, why do I have this 0? Well, we do the coefficients from highest degree to lowest degree. But what are we missing? We're missing an x cubed. So I need what I call a placeholder. So that's what this 0 represents. So we have a 1 for the 1 in front of x to the 4th. We have a 0 because there's no x to the 3rd power. We have a negative 4 because that's the coefficient of x squared, then a 7, and then a 15. So remember, the first thing we do, whatever this value is here, is we drop it down. So I put a 1 here. And then what we do is we take this negative 4 and we multiply by 1. And we put it up here. We have this negative 4. Then whatever we're doing on the inside, we always add, okay? So we're going to add these guys. So now we have 0 plus negative 4, and we get a negative 4. Now whatever on the outside, we multiply by what's in our box. So negative 4 times negative 4 goes up here to positive 16. And now again we add negative 4 plus 16, and this is where we get 12. We multiply again, negative 4 times 12, and that's where negative 48 comes from. Adding gives us negative 41. Multiplying that by negative 4, we get positive 164. And when we add 15 plus that, we get 179. I always box that last number because this is our remainder. And now we have to interpret our answer, okay? So this is our remainder. This becomes our constant. I add an x to each of these. So this has an x, then I go up a power. That's an x squared, and then that's an x cubed. And now we interpret our answer, okay? So we have 1x cubed minus 4x squared plus 12x minus 41. And then the way we write our remainder is plus what our remainder is over what we're dividing by, x plus 4. So hopefully that was a nice reminder for you. Now let's go ahead to the next example. Now we're going to talk about evaluating polynomials. So suppose we have this p of x equals 2x cubed plus 3x squared plus 2x minus 2. Let's suppose I asked you to find p of negative 2. So if I asked you to do this, one way we can do is called direct substitution. Instead of x, we're going to plug in negative 2. So it's 2 times negative 2 to the 3rd plus 3 times 2 squared plus 2 times, negative 2 squared plus 2 times negative 2 minus 2. Then we go through our order of operations, so you can go ahead and do this on your own to verify that you get negative 10. So p of negative 2 equals negative 10. But let's take a look at how can we use synthetic division to help us, or simply synthetic substitution, okay? So another way we can do this is by saying, well, what if we divide by x plus 2? So negative 2 goes in the box. That's kind of like what we were substituting over in example A. I take a look at my polynomial, and my highest degree is 3, then I've got a 2, then I've got a 1, then I've got a 0, so I don't need any placeholders. So now we go through synthetic division. So I drop the 2 down, we do our multiplying, and that's where the negative 4 comes from. Adding 3 plus negative 4 is where negative 1, times that negative 2 is where we get the 2 from. Adding, we get 4. Multiplying, we get negative 8. Adding, we get negative 10. And what do we notice? Okay, what we should notice is the remainder is the same as p of negative 2 when we did direct substitution. So this is called synthetic substitution. So if I wanted to simply find what p of negative 2 is, negative 2 goes in the box, we go through our synthetic division substitution or synthetic division process, and our remainder is our answer. Okay? So that's kind of what leads us to this remainder theorem. All right? So a remainder theorem says if a polynomial, p of x, is divided by x minus c, then the remainder equals p of c, meaning c is the value that goes in that corner. So how do we use this? So let's let p of x be that polynomial from example 2. Let's use the remainder theorem to find p of c when, and I think you need to change this in your notes, let's let c equal 2. Okay, not negative 2, we already did that. Let's let c equal 2. So when we do that, 2 goes in our corner. I double check, do we need any placeholders? And the answer is no. So we have a 2, a 3, a 2, a negative 2. First number always drops right on down. Now we do our multiplying, that's where we get 4. We add, that's where we get 7. Multiply to 14, add to 16, multiply to 32, add to 30. So this remainder is our answer. So p of 2 equals 30. This is a lot easier than actually using direct substitution. It's more efficient. You're not dealing with you're not dealing with powers, okay? So it's a more efficient way to evaluate polynomials, okay? So let's take a look at this next one. All right? So if c equals 1/2, we go through the process. 1/2 goes in our box, goes in the corner. Still don't need any placeholders. Drop the 2, and we multiply by 1/2. That's where we get 1. Add to 4. Multiply 1/2 times 4. That's where we get 2. Adding, we get 4. Multiplying, we get 2. Adding, we get 0. So that means p of 1/2 equals 0. Now let's take it a step further. What this means is if we were to have a factor, that means, sorry, that's not what I want. I want an x minus 1/2. Okay, that means x minus 1/2 equals 0. That means x equals 1/2. And really what that means is that we have a factor, that x minus 1/2 is a factor because what we essentially did was we divided by this polynomial, this binomial, okay? And when we did that, we got a remainder of 0. So that means this factor goes into our original polynomial evenly without any remainder. So that's going to leave us with a factor of x minus 2. So what's so special about a remainder of 0? We kind of just talked about that. That leads us to this factor theorem. Okay, so factor theorem. A polynomial, p of x, has a factor of x minus c if and only if p of c equals 0, meaning when we plug c in, we don't get any sort of remainder. We get a 0 remainder. Okay, so that is, x minus c is a factor of p of x if and only if c is a 0 of p. It's just another way of saying it, okay? So these next examples here, we want to take a look and use synthetic division to determine if the factor theorem, using the factor theorem, to determine whether x plus 1 or x minus 3 is a factor of this polynomial. Okay, so first, I want us to look. Do we need a placeholder for this polynomial when we're using synthetic division? I have got an x to the 4th, 3rd, 2nd, 1, and 0. So no. So now I'm going to go through this first example. Okay? And if I want to see if x plus 1 is a factor, Remember, we kind of do our side note, x plus 1 equals 0, so x equals -1, and that's what goes in our box, our corner, okay? We said we didn't need any placeholders, so we drop the 1, we multiply to -1, we add to -9, we multiply to +9, add to 31, multiply to -31, add to -60, multiply to +60, and we end up with a remainder of 84. Well, what's our conclusion? Well, since p of -1 equals 84, which is not equal to 0, we can make the conclusion that x plus 1 is not a factor of that polynomial p of x. I want you to try example B, okay? Go through the synthetic division, see what your C value is, and make your conclusion. Let's check back. This time around, when I want to see if x minus 3 is a factor, remember 3 goes into the corner, and we go through our motions, and what I got was 0 is my remainder. So my conclusion is, since p of 3 equals 0, that means the factor, or that polynomial, that binomial, x minus 3, it is in fact a factor. Hopefully you got that and you can see the difference. It's all about the remainder, okay? So that's all we have for today. In conclusion, you can kind of look at this final summary here. In the division of a polynomial p of x by x minus c, the remainder is equal to p of c, okay? It's equal to, the remainder is 0 if and only if x minus c is a factor of that polynomial. And the remainder is 0 if and only if c is a 0. It's just another way of saying that term. So if c is a real number, then the remainder of p of x divided by x minus c is 0 if and only if c comma 0 is an x-intercept of the graph of p. Remember, zeros of a function or zeros of a polynomial is just another way of saying x-intercept. If you have any questions, make sure you bring those to class next time we see each other.